Time will explain. Yeah, that's a quote from Jane Austen's novel, Persuasion. Now, you might be wondering, why on earth are we starting an AI explainer with a line from a 19th century novelist? Well, it's because language, whether you're speaking it or writing it, is an inherently temporal thing. It's fundamentally tied to the flow of time. When we talk, we produce a sequence of acoustic events. When we read, we consume a sequence of words that unfolds over time. We even use metaphors for it, right? Like the flow of a conversation or scrolling through a news feed. But for the longest time, early AI had this severe amnesia. It just didn't understand the concept of time. Today, though, we're going to look at the massive breakthrough that changed all of that. Welcome to The Explainer. Today, we are diving deep into recurrent neural networks, or RNNs. We're going to unpack exactly how neural networks finally learned to process the linear flow of time, how they broke free from these rigid, boxy constraints to actually understand language the way we do, as a continuous, unfolding sequence. Here is our roadmap for today. We'll start with the flow of language, unroll the RNN to see how it ticks, and explore how it predicts the next word. After that, we'll look at real-world labeling and classifying, dive into stacked architectures, and finally address a major flaw, the long-distance problem. Let's get right to it.
Section 1. The flow of language.
So, the fundamental problem early neural networks faced was that they could only look at an isolated, fixed-size window of text. Imagine trying to follow a really complex conversation, but you're only allowed to hear 2 words at a time. It'd be completely impossible. Enter the recurrent neural network. By definition, an RNN has a cycle built right into its connections. And this cycle effectively acts as a memory. Instead of a rigid, tiny window, the sequences are fed in one item at a time. The network uses that loop to hold on to information from dozens or hundreds of words in the past.
Moving right along to Section 2, Unrolling the RNN.
Okay, take a look at the dashed line looping back into the hidden layer there labeled H_T. That right there is the recurrent link. In an ordinary network, your input goes in, your output comes out, and that's it. But here, the hidden layer combines the current input with its own value from the exact previous point in time. That dashed line is literally the AI's memory. It encodes everything that just happened to inform the decision that's happening right now.
And if we peek under the hood at the math behind that memory, you'll see 3 main sets of weights. Matrix W handles our current input, and Matrix V handles our output. Standard stuff. But the secret sauce is Matrix U. Matrix U connects the previous hidden state to the current one. And the absolute coolest part is that, during training, the network actually teaches itself how to balance these weights. It actively learns how much it needs to care about the past context versus the current input.
To really visualize this shift, just compare the 2 approaches. On the left, you've got the traditional network cramming a fixed context, like just the last 2 words, into its matrix. But on the right, look at the RNN. It uses its hidden state to maintain a fluid, rolling summary. It processes 1 word at a time and continually updates its internal understanding based on everything it has seen so far. It's so much more dynamic.
So, you're probably wondering, how do we actually train a network that loops on itself? We use a technique called backpropagation through time. Think of it kind of like unrolling a strip of old movie film to look at every single frame. First, in the forward pass, we play the movie forward. We compute the outputs and accumulate all our little errors at each step. Then, in the reverse pass, we rewind the film backward, computing the gradients to update our weights based on the mistakes the model made along the way.
Section 3. Predicting the next word.
Now, a language model's main job is simply to predict the next word in a sequence. If we feed the network this sequence so long and thanks for all, it processes this word by word, building up its hidden state. At the very final step, it uses that rich summary to generate a probability for every single word in its vocabulary. Because it's learned the patterns of English, and hey, maybe it read a bit of Douglas Adams, it correctly predicts that the most likely next word is fish.
To actually hit that level of accuracy, we use something called teacher forcing. It's a form of self-supervised learning where the natural text itself is the label. Think about it. If the model predicts the totally wrong word early on in a sentence, we don't want it to veer right off a cliff using its own bad prediction, right? Instead, we act like a strict teacher putting the training wheels back on a bike. We force the model back on track by feeding it the actual correct history sequence to predict the next word. This keeps the whole training process stable.
Section 4. Labeling, classifying, and generating. What's amazing is how incredibly versatile this core RNN architecture is. On the left, we have sequence labeling. That's where we need an output at every single time step. like identifying if each passing word is a noun or a verb. But over on the right, for sequence classification, maybe we just want to know if an entire movie review is positive or negative. We don't need a prediction for every single word. We just let the RNN process the whole text, grab that final compressed hidden state at the very end, and use that to make one overarching judgment.
And then we have text generation. This right here is the exact mechanism powering the generative AI chatbots you play around with today. It uses autoregressive generation. Basically, the model predicts a single word, and then we take that predicted word and immediately feed it back in as the input for the very next step. It's essentially writing its own context on the fly, sampling word after word until it finally decides the sentence is finished.
Section 5. Bidirectional and Stacked Architectures.
As powerful as a single RNN is on its own, we can actually stack them like building blocks. The output of the first RNN just becomes the input to the second one, and so on. Why would we do this? Well, it's a lot like the human visual system. Your eyes detect basic edges, while higher levels of your brain turn those edges into a face you recognize. Stacked RNNs do the exact same thing with text. The bottom layers catch the basic syntax, while the top layers form deep, complex semantic understanding.
But wait, what if we have a whole document already available to us? An ordinary left-to-right RNN only knows the past. But think about translating a document. The words at the end of a sentence often give you massive clues about the beginning. Enter the bidirectional RNN. We run one network forward, a second network backward, and then just smash the representations together. Now the AI makes its decisions with full knowledge of both the past and the future context.
Finally, Section 6, the long-distance problem. So while RNNs were this massive leap forward, this simple architecture actually harbors a pretty critical flaw. Let's look at this sentence. The flights the airline was canceling were full. The RNN easily predicts the singular verb was right after airline, but by the time it reaches the very end, it has to predict the plural verb were to agree with flights from way back at the beginning of the sentence. In practice, simple RNNs suffer from terrible short-term memory loss. The intervening words completely overwrite the network's local context, and it just gets entirely confused. The simple RNN solved the fixed window problem, for sure, but it hit a total brick wall when context became distant. The memory simply faded way too fast. So, how would you redesign this? How do you build an AI that can consciously decide what to remember and what to forget over vast stretches of time and text? Well, the answer to that question is long short-term memory networks, LSTMs, which ended up revolutionizing AI all over again. But that is a story for our next explainer. Thanks so much for joining us.